Not that many people here. Just a lot of people going on spring break early. Okay, so one thing just to tie up what we talked about. We did improper integrals. You've done a lot of integration techniques. I think we're pretty solid on that. What happens if you have something like this, like for example, 1 to infinity of say 1 over x, and then maybe you have something like the square root of 1 plus 1 over x to the 4th dx, and you have something like that, okay? So, do you want to integrate that? Not really. Yeah, that's a good answer. Not really. So, but you still want to know, does it converge or diverge? And instead of just evaluating it and getting an answer like we were before, what you could do is say, well, I'm not going to figure out exactly what this is, unless maybe it does diverge. For ones that converge, you might not figure out exact. But you're just going to answer, does it converge or diverge? And you can use what's called the comparison test. So the comparison test is going to say the following, is that let's say we have, this situation where f of x, take two positive functions, and let's think of their integrals. Okay, so what could you say if 1 to infinity of g of x diverged? What if the smaller one diverged? What would you think of the larger one? It would diverge, right? It would diverge, yes. Okay, so if the smaller diverged, the larger would diverge by a basic comparison. Because in other words, if the small one, if you integrate, it's strong enough to get you to infinity, well, the large one, when you integrate it, you'd expect it to have more area. Well, it's going to be infinite. So in other words, you could say that if the smaller diverges, then the larger diverges. Okay? What could you say if the larger converged? What if the larger one converged?
The smaller one converges too?
Then the smaller one would converge. Okay? So we know that 1 over x diverges, right? 1 over x from 1 to infinity, 1 over x, we know by the p-test that this diverges. Well, isn't this slightly bigger than 1 over x? I mean, this is, when x is 1, this is going to be 2, but that's the square root of 2, but otherwise it's going to be square root of 1 plus some tiny positive number, right, as x goes on its way from 1 to infinity. So this will diverge by the comparison test. Okay, this will diverge by the comparison test. Similarly, we could, let's give an example of something that converges. So for example, we know that 1 over x squared converges. So what if I just did the same thing and I put something down here like, 1 to infinity of 1 plus 1 over, x to the 8th, something like that. Okay? So if you look at it, this function, in other words, we know that 1 over x squared is slightly bigger than 1 over x squared times the square root of 1 plus 1 over x to the 8th, right? Positive on this interval, right, from 1 to infinity. So we know that this function converges. So in other words, 1 to infinity of 1 over x squared converges is actually equal to 1. We've already seen that. So what does the comparison test tell us about this? If the larger converges, the smaller converges. Now, that doesn't tell you what it converges to, right? It doesn't give you an answer what it converges to, but it tells you it converges. You know it's finite. And you know it's bounded by 1. So, somewhere between 0 and 1. You're not going to know exactly yet.
Wait, why 1? Why 1?
Well, because this integral here is 1.
Oh, okay.
Yeah. So you know that this one's not going to be bigger, right? Because it's smaller. The area is smaller, right? So you know that you're not going to figure out what it is exact unless you want to go and actually integrate that and do the limit and go through the whole thing. Yeah. So this is a kind of a convenient way to at least answer the question of is it converging or diverging by the comparison test. So this is a comparison test for integrals. Now there's an even stronger test called the limit comparison test. And the limit comparison test would be kind of the same situation, except what you have now is that you're taking a limit as, say, x goes to infinity, and you're looking at, say, two functions like, f over g, okay? And let's say they're roughly some positive constant, okay? So they're in the limit, they're a positive constant, which means that roughly when x is getting big, this is about c times, f is about c times larger than g. Well, it depends what c is. C could be quite small, in which case g might be larger, but the ratio between them will be c. So in this case, if you do have a positive constant, then the limit comparison test is going to say that this integral from 1 to infinity of f is going to converge if and only if this integral from 1 to infinity of g is going to converge. In other words, they will do the same, they will have the same behavior. And the intuitive way to think about this is that, let's say, let's give let's say c is 5 or something. That says f is roughly got 5 times as much, if you look at the area under that curve, 5 times as much as g. So if this is a finite number, well, this is a finite number too. It's just, yeah. So that's a way of thinking about this. Now the other part of the limit comparison test would be, so this would be like part A, and then part B, okay? let's say that we take this limit, and so this is case A. Okay, let's say in case B that, so let me write my case over here. Where can I write? Let me write it up here. Okay. Staying on this one board. Okay, so what about in case B? What if the limit as x goes to infinity of f of x over g of x was 0? What if that happened? Which one would be the larger one? G. G would be a lot larger. Okay? So if, let's say G was your, let's say you knew something about, let's say you had some known information about G. And you were trying to get information about integrating F. So let's say this was known to you. And you wanted to get some information about this. Okay. What could you then say?
The ratio
Well, let's say you knew something about this. Let's say you knew something about that. You wanted to know about F. Now I'm claiming there's partial information. You know that F is a lot smaller than G. They're both positive. They're both positive, but the ratio is going to 0. So you know G is getting a lot larger compared to F. So if we knew that that integral converged, what would you know about F?
It would also converge.
It would converge. So in other words, you would get an answer here. You could say convergence here would give you convergence here. Convergence for G, right, would give you convergence for F. Okay, but what if G diverged? Would you get information? In other words, would you get information at that point? G is a lot larger. It happens to go to infinity when you integrate it. Would you necessarily get information?
No.
No, you wouldn't get information. You still wouldn't know, right? Yeah.
So for B, it's only when it equals 0?
Part B is equal to 0. And then part C would be what happens if this is infinity? Then what do you know? F of x is a lot bigger, yeah. F of x is a lot bigger. So G is the one you have information. So if G converged, would you know anything about F converging? No. But what if G diverged? Yeah, then you would get information that if you had divergence for G would give you divergence for F. Okay? Now, don't worry about this so much. It's not going to be on the midterm. But, it's just to know. We'll see it later when we get to series. Okay? So I'm just tying up some loose threads. let's do some differential equation. Okay, so for a differential equation, we're going to do what's first called a separable differential equation. All right, now this is called a separable DEQ. Now the first thing you got to realize about a differential equation, the variable is a function. Okay, the variable y is a function of x. So when you see something like a differential equation that says, you know, y prime is equal to xy, right? Solve for y. Okay, you have to think what's going on. So what you think is that y prime of x is equal to x times y of x. In other words, y is a function of x. It's an unknown function of x. And you're trying to now solve for a function. Okay, your previous experience, I think, with variables, whenever they say solve, is solving for a number, right? You learned like quadratic equation, right? You know, ax squared plus bx plus c equals 0. And you were solve for x, right? You're trying to find a real number. Here you're trying to find a function. What function has the property that its derivative is equal to x times itself for all values of x in its domain? So this is a question about finding a function. Okay? Now, we're going to use a little trick to solve something like this. Okay? And the trick, and I'll justify the trick after I show you the trick. So I'm going to show you the trick, and then I'm going to justify the trick. Okay. So we're going to use the notation dy over dx for y prime. We're going to use this notation instead of the prime notation. I'm going to rewrite it like this. And I'm going to let's imagine and just pretend that we can multiply both sides by dx and bring the dx over to the other side. And then I'm going to divide by both sides by y. So in other words, I'm going to get the y over on the left-hand side with the dy. I'm going to move this over. It looks like I'm multiplying by dx, but I'm just kind of moving it over there. I'm getting 1 over y dy is equal to x dx. Okay? And now I'm going to integrate both sides. Now we know when I do that, I get, you know, like x squared over 2 plus, you know, c. Now what happens when I integrate 1 over y? What do I get? ln absolute value y. Okay. So now I've got x squared over 2 plus c is equal to ln absolute value y. All right, I've just got to get rid of ln. How do I get rid of the ln? Right, I use the inverse function. So in other words, I take e raised to this is e raised to this. Okay, so in other words, e to the x squared over 2 times e to the c is equal to absolute value of y. And now I can say that y is equal to plus or minus e to the c, e to the x squared over 2. Okay. And what is e to the c?
What's C?
Hmm?
C. It's a different constant.
Yeah, it's just a different constant. I mean, e to the c is any positive real number, and then you have plus or minus, right? So you've got any real any non-zero real number. Why don't we just call that big A or something. So let's have big A be plus or minus e to the c, because c can be anything, so plus or minus e to the c we'll just call real number A, and we will say that this can be A times e to the x squared over 2. And that's the solution. And you could check it by just differentiating it, right? So if you differentiate it, here's your y is a e to the x squared over 2. If you differentiate it, y prime would be a. This would be chain rule, e to the x squared over 2 times the derivative of the inner. Now the derivative of that inner function, well, we all know that that's just x. So it is itself times x. Well, that's what you wanted, right? So you solved it, right? Now it looks like it's a little bit of a trick, and in some sense it is, but let's go through it. And since I'm stuck on this board, I have to erase this board because we're going to go over here. So I'm going to erase this, but then we're going to go through the justification. Now that's kind of what you have to do. But let's go through the justification and we'll do some more examples. Okay, so a separable differential equation looks like y prime is some function of x divided by some function of y. Okay? If the differential equation has this form, or it can be written in this form, then it's separable and you're going to use this trick. So the trick you're going to do is you're going to use this form, dy over dx is g of x over h of y. You are then going to separate. So you're going to separate. In other words, you're going to get the g of x with the dx, and you're going to get the h of y with the dy. So you have to get all the y's and dy's on one side and all the x's, dx on the other side. So you're going to, looks like you're crisscrossing, so you're going to do h of y dy is equal to g of x dx. Okay? So you're going to separate, and then you're going to integrate. Step 2 is you integrate. So it's a two-step solution. You separate and integrate. So then you integrate h of y dy is equal to, I'm going to take the antiderivative of g of x dx. And so you separate and integrate. Okay? All right. Now, what's the justification for this? Well, it really is your substitution rule. Okay, so your substitution rule, remember what your substitution rule says. It says, for instance, if you have some function, and I'm going to call this, say, f of x or something, okay? And you give it a name like y, okay? And then you have something like h of f of x times f prime of x dx is equal to the antiderivative of h of y dy. Okay? That's your substitution rule, right? That's what you learned when you do u sub, right? Or here we're doing y sub, right? So this is your substitution rule. Let's write it a little bit better. Here I'm on camera. I have to be very precise. H of y dy. Okay. Now, the only thing we're going to do to justify this trick is I'm going to rename, instead of using f, I'm going to use y of x. In other words, I'm going to use this notation. It's going to look a little bit like an abusive notation, but I'm going to use y of x is equal to y. And in this context, y is a function name, so this instance is a function name. And this instance here is a variable name. And if I apply my substitution rule, in this context, I get h of y of x times y prime of x, the antiderivative of h of y of x, y prime of x dx, is equal to the antiderivative of h of y dy. Okay? So this is just here, this is just your substitution rule. That is just your substitution rule. However, we have that y prime in the separable differential equation. Y prime is g of x over h of y. So I can substitute g of x over h of y in for this expression right here, the y prime. And when I do that, what do I get? I get the antiderivative of h of y of x times g of x over h of y dx is equal to antiderivative of h of y dy. Well, these are just canceling because they're the same thing. Remember, y is a function of x, so h of y of x, h of y of x, they're canceling, and you get antiderivative of g of x dx is antiderivative of h of y dy. That's why it works. It works because of the substitution rule. Okay? But you'll just, in practice, you'll think of it as a trick. You'll act as if, I'm multiplying both sides by dx. Okay, you're really just doing the substitution rule, but you get to think that way, yeah.
So the bottom h of y is h of y x? Oh,
Yeah, y is a function of x.
Oh.
Yeah,
Dr. Goldman,
yes.
so can we get an example or something like that?
Yeah, so we're going to do more examples, yeah. So let's do some more examples. Okay, so okay, dy dx or y prime is equal to 3x squared e to the minus y. 3x squared e to the minus y. Well, is it separable? It's the first thing you're going to ask is it separable? Yes, because it can be rewritten as 3x squared over e to the y. Yeah? This is y prime. So it is a function of x divided by a function of y. So what I'm going to do is use the notation dy over dx instead of y prime. I'll make use of this convenient notation here for the derivative. And I'm going to set that equal to 3x squared over e to the y. And then I'm going to separate and then anti-differentiate. So I'm going to separate and anti-differentiate. So I separate, in other words, I get e to the y dy is equal to 3x squared dx. So I separate. now integrate. Okay, so antiderivative e to the y dy is equal to antiderivative 3x squared dx. Okay, so I separate and integrate. Okay, you know this is just e to the y. And this is what? X cubed plus c, and then y is going to be ln of x cubed plus c. Okay, this is a separable differential equation. You separate, integrate. Now I'll give you a let me give you a nice example in biology where this is useful. Okay, so I'll give you a biology example. So in biology, there's something called logistic growth. And logistic growth happens when you have a population that has a finite resource. So in the beginning, there's a lot of reproduction happening. They're growing very quickly, but then they start to use up their food supply, or the natural resource, and so then they start to die, and the population growth starts to slow down. Okay, so something grows logistically if it grows according to the logistic differential equation. So let's have n of t be the population size at time t. Okay. And a logistic growth model, there's going to be what's called a carrying capacity. The carrying capacity is the maximal sustainable population. It can't ever get beyond the carrying capacity. So because of the limited resource. So let's say M is the maximal sustainable population. It's also called the carrying capacity. Maximal sustainable population, or the carrying capacity. So we're going to say that the rate of change of growth, dn dt, that's the rate of change of the population with respect to time. Okay, the rate of change of growth is going to be proportional to how many animals are in that population, whether it's animals or fish or insects or whatever. So it's going to be proportional to n. It's some constant, say k times n. But it's also, you also have to look at 1 minus n over n. In other words, this factor here is kind of a deterrence, because if you think about it, if n starts to get big and approach to m, this is almost 1. So 1 minus something almost 1 will be small, and that will slow down the rate of change in the population. Okay, so you have sort of, this is tending to push this up, and this is tending to slow it down. This is speeding it up, that's slowing it down. So we want to get, that's the kind of classic differential equation for logistic growth, and we want to solve for n, we want to figure out what n is based on this, okay? So what we're going to do is, it's separable, so we're going to separate and integrate, and it's going to be a partial fraction. So let's see what happens. So let's rewrite this as k n, and let's write this as m minus n over m. So I'll put this constant here, m is the, so I'm going to rewrite it in this form. So it's m minus n, k over m. Okay. So let's separate. Let's get the n's on that side, and let's get the dt on this side. So we're going to separate. In other words, we're going to get 1 over n, m minus n. And I think I'll multiply the m over here. So let's put the m over here, dn. And then over here we'll just have the k dt. So in other words, I moved all of this over, but I left the k, and then I moved the dt over to go with the k. Okay. So let's we separated it, so let's anti-differentiate it. So we separated it. Let's integrate it. So this is going to be a partial fraction, right? This is going to be a over n plus b over m minus n, right? And that's going to equal m over n, m minus n. So what are you getting? Do the partial fraction for me and tell me what a and b are.
Is B1 and A1, 2?
A and B are one.
Yeah.
They're one?
Yeah.
You're getting one?
Yeah, both
Okay.
are one.
All right, let's check. So a m minus a n plus b n is equal to m. You can think of this as 0 n plus m. So we've got b minus a n plus a m is equal to 0 n plus m. So a is clearly 1, and then since b minus a is 0, b is 1. Okay, very good. All right, so let's rewrite this now. So erasing this. I'm going to rewrite this now as the integral of 1 over n plus 1 over m minus n dn is equal to integrating k dt. Okay. So what happens here? What's the antiderivative of 1 over n dn? ln, okay? ln, these are going to be positive, so we'll just put n. And what about the antiderivative of the other?
So ln of n
And
minus n.
minus
gonna be, is it ln of n minus n? Chain rule. You're missing one thing.
Oh, negative.
Minus the derivative of the inner, yeah? There's that minus n. And so if you differentiate m minus n, you get negative 1. So you have to compensate for the chain rule. Yeah? So this is going to be minus ln of m minus n. Okay, this is just going to be like kt plus c. Okay? And then this is just going to be what? This is going to be ln of n over m minus n. And this is going to be kt plus c. And now how do we get rid of it? E to this, e to this, e to that. So in other words, n over m minus n is going to be this e to the c, e to the kt. We'll just rename this a e to the kt or something like that. Okay. So now we just have to solve for, n. So let's do that. Okay, so I gotta get some room. So I'm going to erase this and get some room here. Okay, since we're on this board. Okay, so I'm getting n is equal to a e to the kt times m minus n, which is a e to the kt m minus a e to the kt n. Okay, and that's equal to n. Okay, well I want to get the n's all on one side. Yeah, so I'm going to add this over and move it over here. So I'm going to get n plus a e to the kt n, which I can factor, has n times 1 plus a e to the kt, and that's going to be equal to this. Because after I add it over, I've just got that. So I've got a e to the kt m. Okay, so I add it over, factor it, and set it equal to the new right-hand side. So once I move this over here, my right-hand side is this. All right, and then all I do is just factor it. And now all I have to do is divide by this. So I'm going to get n is a e to the kt m divided by 1 plus a e to the kt. Okay? And there's a solution. Now that's not usually the slick form that they like it in. So usually what they do is so n of t is a e to the kt m over 1 plus a e to the kt. Usually what they do is they multiply both sides by a to the minus 1 and e to the minus kt. So we're going to just multiply by 1 in the form of a to the minus 1 e to the minus kt over itself. Okay? And when we do that, this wipes out here and just leaves m in the numerator. And this becomes a 1 when it hits this. And then when this hits the 1, it just becomes a to the minus 1 e to the minus kt. Let's call a to the minus 1 b. Let's just give it a name. And so we've got b e to the minus kt. And this is the normal form. That's kind of the usual form that you see logistic growth written in. That would be the solution. Okay? Some constant times e to the minus kt. Now you can figure out what that constant is. In other words, it's not hard to figure out what that b is from the initial condition. So the initial condition will be that your starting population is called n naught. This is your starting population. And so if that's your starting population, you know that n naught is going to be m over 1 plus b e to the minus k times 0. But what's e to the minus, what's e to the minus 0? What is this?
1.
Just 1. Yeah, so this is m over 1 plus b, so solve for b. So in other words, 1 plus b n naught is equal to m, so b is equal to m over n naught minus 1. In other words, it's your maximal population over your starting population minus 1. So another way to fully express the logistic equation is to say that the population at time t is the maximal carrying capacity divided by 1 plus the carrying capacity divided by the initial population size minus 1 times e to the minus kt, where k is the positive constant that appears in the original logistic growth differential equation, which is there. Okay, that was the original differential equation, and that's the solution. Okay? Now what do solutions like that, what do they look like? Well, they look kind of like this. So I'll erase everything, so I'll put this here, so the ndt is k n 1 minus n over m. Okay, so this is the differential equation, this is the solution. So this is the solution to the logistic differential equation. This is logistic growth. And what does logistic growth look like? Well, you can kind of see that what happens is, what happens when t goes to infinity? In other words, what's the limit as t goes to infinity of n of t?
It converges.
To what? As t gets big, what happens to e to the minus kt?
It's gonna be, minus negative.
Goes to 0, right? So when t gets big, this, I'll use a different color. This is going to go to 0, which is going to wipe this all out, and you're just going to have m over 1, right? So it goes to m. And that makes sense. That's why there's a horizontal asymptote at m. So if you plot time and you plot population size here, you'll start somewhere at n0, and it will grow up rapidly, but then it will start to approach this horizontal asymptote, which is at the carrying capacity m, and that's what typically a function that has logistic growth, that's kind of what it looks like. Okay, so logistic growth is just a separable differential equation solved with partial fractions. That's basically what it is. Okay. Now there's a second kind of differential equation that I'd like you to know. It's not in the book, but I think it's really easy, and it makes for an easy midterm question, so I'm going to give it to you. It's really easy. And so all you got to do is just learn it. There's a trick to it. So these are called second order linear homogeneous. Okay, and they look like this. They're always of the form like A is just a constant, y double prime plus by prime plus cy is equal to 0. And these are like the easiest thing to solve. Okay, so there's a nice trick to it. All you got to do is substitute r squared in for y double prime, substitute r in for y prime, and then just ignore the basically substitute 1 here. Just think of this as c. And just look at this equation, ar squared plus br plus c equals 0. And solve it for r. Just solve it for real number r using the quadratic formula. Okay? So solve this. And there's going to be 3 cases, right? There's 3 things that can happen. What are the 3 things that can happen when you solve any equation, anything you're using the quadratic formula on, an ar squared plus br plus c? There's 3 things that can happen.
You have 2, 1, or no solutions.
2, 1, or,
Imaginary.
well, you have an imaginary solution plus its conjugate. Okay, so the 3 things that can happen are 2 real distinct roots. So 2 real roots you can get an R1 and an R2. The second thing that can happen is you can get just a repeated real root. In other words, 1 repeated real root. Which is R1. And then the third thing that you can have is you can have like an alpha plus minus beta I as a solution. Right? You get a complex number and its conjugate. Okay, so there's 3 cases. And then those 3 cases determine the answer. So the answer is going to be, for the first one, very easy, it's going to be e to the r1x plus e to the r2x, and the general solution, you can have any constant here, c1, and any constant here, c2. Okay, and that's the general solution for y. And in the second case, it's very similar. It's going to be e to the r1x, but here you get to throw in an x. So when you go to the next one, you throw in an x and repeat e to the r1x. And that's the solution. And when you go to the third case, now the third case is I can justify these 2 cases for you now. The third case, you're not really going to understand until the end of the class. So remember, we're going to come back to this when we do Taylor series and when we do the expansion for the series expansion for e to the x, and then we're going to understand it. And we do cosine and sine. We're going to understand where this comes from when we look at series. But for right now, I'm just going to give it to you. The solution is going to be e to the alpha x times, it's going to be c1 cosine of beta x plus c2 sine beta x. And all you have to do is just memorize these. Yeah? Really easy. Right? It's always going to be that way. Okay, let's try a couple of these and I'll just show you how easy they are. Okay, so let's do them over here. So they're really easy. So make for easy questions on a midterm. Okay, so and you'll learn them later. You'll learn them later in more detail when you take a differential equations class. But I'm throwing them into our class, even though Thomas doesn't have them. Most calculus books throw them in. Most calculus books even show you variation of parameters. This book doesn't for some reason. So, but I think they're really easy. So let's do something like y double prime minus 3 y prime minus 28 y equals 0. Okay? So, really easy. All you do is r squared minus 3r minus 28 is 0, r minus 7, r plus 4 is 0, r1 is 7, r2 is negative 4. Your answer is c1 e to the 7x plus c2 e to the minus 4x. Is that easy? It's just going to be like that. It's a nice trick.
So after you solve for r, you just plug in r.
Just plug them in, you raise e to the power of that root times x. Yeah. So let's, you want to see why this, you want to see the justification at least for part A. So let's say that, so this is your equation, like ay double prime plus by prime plus cy is equal to 0. Okay, so we claim that this is a solution. Okay, so we have like, we do like ar squared plus br plus c is 0. And we're claiming the solution. Say y is c1 e to the r1 x plus c2 e to the r2 x. Okay, well, let's check that this really does work. So in other words, let's take the derivative. So what's the derivative according to the chain rule? What's the derivative? So differentiate y.
Is it CR1 ER1X?
Yes. C1 R1 e to the R1x, and this is going to be C2 R2 e to the R2x. And then
You derive it again?
let's take the second derivative. So what's the second derivative?
You do the same thing, multiply by R1 and then multiply by
C1 R1 squared e to the R1x plus C2 R2 squared e to the R2x. Okay? Now let's multiply this by A. So A y double prime is, I'm sticking an A here, I'm sticking an A here. Let's, actually I should do that in a different color probably. Let's insert the A here in green, so you can see it a little bit better. So put the A here, just put the A here, put the A here. Let's put the B here, and let's put the B here. Let's put the B here, and let's put the C here, and let's put the C here, let's put the C here. Okay? Now, I wanna add them up and check that I do get 0. Right? Because when I add these up, so when I add these all up on the left-hand side, I get 0, right? Because that was my supposition, that was my assumption, that was the starting point. I do get 0. Well, we want to check that does this actually give 0, and we'll see why it gives 0 and what it has to do with this. What does it have to do with that? Well, let's add it up. So I'll just add it up by these two columns here. So when I add up this first column, what is common to to all three terms? What's common that I can factor out?
C1, ER1.
Yeah, C1 E R1X. So I've got C1 E R1X, and then I can factor, what have I got? I've got C plus BR1. So I've got C plus BR1 plus A R1 squared, yeah? But if R1 is a solution to the quadratic equation here, what is this? 0. So that wipes it out. And now if I add this up, we similarly we factor out the C2 e to the R2x, and now I've got, and I'll put it in green, I've got C plus B R2, and I've got A R2 squared. But R2 is a solution to this equation, so this is 0, so it wipes out and it works.
But C doesn't cancel out. Does it? How does the C disappear inside the green?
R squared plus BR plus C is 0.
Oh, okay. Okay.
We're assuming that R1 and R2 satisfy that equation.
Okay.
Yeah. That's R1 and R2 satisfy this equation, and we get them from the quadratic formula. So that's the justification there. Okay, now the justification, I'll tell you what, for extra credit, try to work out the justification of why you have the X here. You'll have to do, when you take the derivative, there's going to be a product rule. Okay, and all you have to do is account for the product rule. And for extra credit, try to justify in the same way that I just did here, by looking at these columns and making sure they're 0. Try to justify why you have to throw in that X. I'll give you a hint. If you do it with 3 columns, 2 of your columns will easily be 0. You'll see that right away. The second one, you have to think of the differential calculus, and some of the rules for local min. Local min and differential calculus. Local min and max, that type of thing. Okay, so think of, that'll be the hint, but try to justify this. This last one, I will justify on maybe the last day of class. So at the very end, right before the final exam, I'll derive this for you. I'll show you where it comes from, but we need to go through series, so maybe end of April I'll do this. Okay, and that gives you, now you know how to solve some differential equations. So the rest is we're going to practice. So now you practice for the rest of the class. I'm just going to list some differential equations on the board. You practice, get them. Okay, so I'm going to put up some separable ones, and I'm going to put up some of these second order homogeneous ones. Okay, so 2 square root xy dy dx is equal to 1. Solve. Remember, you're solving for y. Y is y is a function of x, so you're solving for y as a function of x. Y squared dy dx is equal to 3x squared y cubed minus 6x squared. Okay. So try these two with the separable method, separate and integrate. And then I'll give you two of these, so why don't we do one with, we'll do the other two cases, get you to practice. So maybe y double prime plus 4y prime plus 4y equals 0, solve this, and solve this one. Y double prime plus y prime plus y equals 0. Solve these. You could probably pause that thing, while you're working on this stuff. I don't know if it's- Maybe just leave it if I'm not sure. Yeah, I don't want to mess it up, but this is intermission in effect, right? You're just working on them. And then when you get a solution, we'll put your solutions up. See how you do. Done?
That's the first
Is that the first one? So Patsy, you wanna tell me what you did with one?
So root x will go to the other side and
Okay,
integrate.
so you're dividing by it, you wanna divide by it.
Yeah,
Okay.
this side I have
2 root y,
y
okay? 2 root y dy,
Y.
good,
equal
is
to
equal to
1 over root x
1 over root x, yes, beautiful. Okay, and then you integrate. And what's the antiderivative here?
is negative 1 over 2. Oh no, it should be
Square
or
root.
positive 1 over 2.
Root x
Root,
Oh,
root
half.
x over
times,
2.
Huh?
Oh, root x.
times 2, right?
Yeah,
This is 2 root x, right?
yeah,
Yeah?
yeah.
Okay, so 2 root x plus c, and what do we have here? What's the antiderivative here? No, antiderivative. So y to the half, what do you have to do with y to the half?
Oh,
So
y to
is
three
it
half.
4 square root
Negative
y cubed
2.
over 3?
Say it again?
So is it 4 square root y cubed over 3?
Y cubed.
Or
Y.
square root, yeah.
Y to the 3 halves.
Y to the
Oh,
three
the
halves.
square root,
Yeah,
yeah,
yeah.
y to the 3
Yeah,
halves,
square
square
root,
root,
y.
okay, yeah. So it's just, the antiderivative of y to the 1 half is y to the 3 halves times 2/3, but then you've got the 2, so it's 4/3 here. Okay, so it's that, and then you're just gonna, I guess, throw this on the other side, so y to the 3 halves is equal to, you're gonna multiply by 3/4, so what's that, 3 root x over 2, just rename your constant, I don't care what it is, call it a. And then, how do you undo it?
This is opposite. You
Y is equal
square and
to,
then you cube it.
yeah, so this to the 2/3. Yeah. Yeah,
Yeah.
yeah, very good. Looks good to me. Okay, on number 2, you gotta make sure it's separable first, is it?
No, not yet.
It is, but you gotta do a little work. What do you have to do?
Factor here.
Yeah, you gotta factor first. So in this, you gotta factor. So in other words, you've gotta get it y squared dy dx is 3x squared y cubed minus 2. Now it's a multiplication. and now it's separable. In other words, it's in the separable form where this is 3x squared over, you could divide, first of all, you could get this on the other side by putting the y squared here. And then you could think of this as y squared over y cubed minus 2. So it's in that separable form of a function of x divided by a function of y. Okay? So you want to separate and integrate. So in other words, you want to integrate y squared over y cubed minus 2 dy is equal to the antiderivative of 3x squared dx, okay? What's this? What's the antiderivative here? You can do this in your head. What is that?
Or use of.
Yeah, just do it, use up, don't do the, you could do a partial fraction, but this is much quicker, yeah. So this is just, you have the derivative there as long as you put a 1/3 out here. So anti-differentiate the outer, so the outer function is 1 over y, it's going to be ln of y cubed minus 2 and over 3. Yeah? It's going to be the antiderivative there, and then this is just going to be x cubed plus c. And so then we'll do the trick, yeah, we'll get the 3 over, so we'll get ln of y cubed minus 2 is 3x cubed, let's call this a, rename the constant, and then do e to this and e to that. And so this is going to be y cubed minus 2 is going to be e to the a, e to the 3 x cubed. Let's just rename this, call this b or something. Okay? And I guess there was a plus or minus because we could have then called this y cubed minus 2 is plus or minus e to the c, e to the 3x cubed. Just rename this some constant. Okay? And so then add 2 to both sides and take the cubed root. So y is going to be the cubed root of a e to the 3x cubed plus 2. Like that. Okay. Now what about these last two? What's this one? What's the root? 2?
Whoa, what? Root?
Yeah, what's the root of that quadratic equation we come up with for the trick? Yeah, what's the root? What's r?
Minus 2.
Negative 2. Yeah, negative 2. So what's the solution?
C1 e to the minus 2x.
C1 e to the minus 2x plus
C2
C2x e to the minus 2x. Very good. And if you solve this one, what's your complex root? So r squared plus r plus 1. What's the root? Equals 0. What's r? Minus 1 plus minus square root of, what am I going to get? What's b squared minus 4ac?
-3.
Negative 3 over 2, yeah? So it's going to be, in other words, it's going to be minus a half plus minus root 3 over 2i. gonna be your alpha plus minus beta I. So what's your solution? So alpha is minus a half and beta is √3/2. So what's your solution?
E to the minus of half x.
E to the minus x/2, C1 cosine
cosine.
√3/2x plus C2 sine √3/2. Beautiful, okay? You did a lot today. Very good. Okay, enjoy your spring break. And we'll be back at this on 14th. Ronnie will be visiting. And we'll kind of repeat a lot of this stuff, but we'll work on some more differential equations. Wednesday, Friday we'll review, and Monday we'll have our midterm.
So that one, e to the power a becomes b, and then I don't know what's going on or something.
Oh, I just said, you can rename those constants, right? It's like, I guess I should have called this, instead of C, it's just A. So all I was saying was that I should have had the absolute value here, so if you keep the absolute values when you take e to both sides, you just get the absolute value is equal to e to the a, which I'm calling b, but then I should have said this becomes this, if we remove the absolute values, it just becomes plus or minus b e to the 3x cubed. But then I can rename this, something. Whatever you want, big K, I don't care, just rename it. It's just a constant, it doesn't really matter. Yeah? Yeah, so it's like C could be anything, right? So e to the c can be anything. And then plus or minus e to the c will be anything. So you want to rename this b and rename this plus minus b and call it a, or whatever you want to call it, k. Just renaming the constant, right? Basically anything. Not really. I guess I should have said plus minus b here. You can turn that thing off so that I don't look